All right, thank you very much. All right, so as we've been hearing recently, there's been this huge explosion in the number of lithium-rich red giant discoveries, which is really exciting because these things are rare. So it really needs these really large surveys to be able to find so many of them, since they do represent only a few percent of the red giant population. You guys hear me okay? Okay. All right, so we've seen variations of these plots before with some of these large surveys, such as, the Limos survey and the Glass surveys, where you can see how lithium generally decreases as red giant evolution occurs, but you have these nice clumps of these lithium-rich stars, which you can see here in both the Limos and the Glass surveys. And on these plots, you can see some of these traditional definitions that we use to define what lithium-rich is here on this survey from Kumar et al. And from Martel et al. Looking at lithium as a function of broadening, we see some of these definitions of super lithium-rich and regular lithium-rich. But of course, when we're talking about what is lithium-rich, really what we're using this is to encode a sense that something has gone differently with stellar evolution. And we've heard now a lot of times this classical lithium-rich definition that comes from very early understanding of what happens with lithium dilution. And then super lithium-rich, it's telling us that something truly additive must have happened to these stars, that they're exceeding some primordial value, whether it be the primordial solar system value as we measure for meteorites, or even what came from Big Bang nucleosynthesis. But as we've heard now from a number of talks, this classical definition is really too simplistic, right? So even when you look at the current solar value for the lithium abundance, it has not yet gone through its red giant stage. It has not gone through dilution. And a value of 1.5 is not going to pick up if something unusual has happened to the sun. And so thankfully, lots of other talks have talked about all the complexities of what happens on the pre-main sequence. And by the time you get to the main sequence, we do know that there are trends with how old these stars are, with how massive these stars are. So these are just showing plots of main sequence lithium in an open cluster and for a large population of field stars. And you can see that there's a huge variation of the lithium abundances that we see. And we do know that mass is a very strong indicator of how much lithium we would expect in a star. So by the time you get to the red giant phase, all of these masses are now kind of all grouped together. So in these large field studies, we know that there's going to be a large amount of variation just in mass. So the work that I'm going to talk about today is work that I did with collaborators, many of whom are in this room, trying to define what normal lithium is so that we can define what lithium-rich is for stars at different masses. And to do this, we relied on stars in the APOCAS sample, which combines stars that have been observed with the apogee spectrograph and stars that have Kepler acid seismology. And what this allows us to do is get a really good sample where we know the mass of the stars, and we can select stars across a large range of masses. And to also be sure that we have a good sampling of both stars that are on the first ascent red giant branch and are in the red clump. Additionally, we kept a relatively narrow range of temperatures of these stars. So the temperature is a very strong indicator of the lithium line is very sensitive to the temperature. So the strength of the line depends strongly on that. So we narrow that as much as possible. And we also narrowed the metallicity range of our stars. So our sample here is just showing the log G and temperature of those stars with our red clump sample in blue and our red giant branch in purple. And just for reference, I grabbed a plot from the Santaki et al.'s paper just to show how narrow of a region this is. Additionally, we also have some known lithium-rich stars in our sample that we added, and stars that have known either surface or rotation speed. But I won't be talking about those very much until the very end. Now, apogee does not cover the optical range, so we went ahead and obtained optical spectra from the Subaru data, from the Subaru telescope at very high spectral resolution. And I like to show plots every time I measure lithium so you can get a sense of what this looks like. And I cherry-picked two of the stars in our sample to make two very specific points. So on this plot here on the right, I'm showing the lithium abundance where the lithium line strength is actually relatively similar to the neighboring iron and carbon CN blend. Now, you saw in some of the other talks that when lithium is very strong, it becomes the dominant line. But as you get to lower and lower values, you have to start worrying about blending. And this one I cherry-picked because we found when we were comparing our lithium abundances to stars that overlap the Limos data, we get very good agreement for stars that have very high lithium abundances. But once we start getting down into what we think is the detection limit of Limos, we actually start to see divergence. And there are some stars where Lemmost is claiming lithium detections, where we at higher spectral resolution are actually finding that we ourselves still cannot measure lithium, that these are actually upper limits in our survey. So you need to worry about when you're at your detection limit. And for us, on the bottom here, I'm also showing where we're starting to approach our detection limit with our data. And here, what we really had to worry about is what the carbon nitrogen abundances are. So we did have carbon and nitrogen from Apogee, from the Apogee Spectra, from the ASP-CAP pipeline, all these acronyms. And we were hoping to use that to constrain them, but you'll see here in these model plots, which all have the same lithium abundances, but different assumptions for the carbon and nitrogen ratio. Had we adopted walking out of the Apogee spectrum, we would have had to artificially increase what we thought the lithium abundance was to get that out. So you have to, so that's something that you do need to worry about. Okay, so what did we find? So remember, the point of our sample here was to try to get a sense of the lithium variation as a function of mass. And we found that we actually, even in our individual mass bands, we see a large amount of variation. So the color coding here is discriminating between our red clump stars and our red giant branch stars. And you see some of the expectations that you might expect, such as for the higher mass stars, when we detect lithium, we do tend to detect higher lithium abundances, which makes sense because we know that those stars on the mate sequence tend to have more lithium. But I want to highlight that the vast majority of stars in our data, we actually don't detect anything. It is below our detection limit. And this is true in every mass band that we looked at and in both the red clump and in the red giant branch on the first ascent. Now, qualitatively, this is consistent with the results from Shanmei et al. That was looking at how much dispersion you might expect if you had simple stellar models just drawing from the large dispersion that you see in the main sequence. So that gives these predictions here for what you expect for the red clump stars. And you can see that this upper limit here is roughly consistent with the upper limit of where we're seeing detections in our sample. And then for these are color coded by mass. And so you can see that the lowest mass things have the largest dispersions. And you expect them to be to have extremely low lithium abundances. The other thing that we could do is try to see if we have any expectations on how lithium is changing between the first ascent and when it reaches the red clump. And to do this, we just simply looked at the difference by how often we detect lithium at any level compared to when to our non-detections. And for the lower mass stars in our bin, we find that we actually detect lithium just as often at the red clump as we do in the red giant branch for the lower masses. But for the higher masses, we tend to detect lithium on the first ascent in these higher mass bins, but then by the time you get to the red clump, but many fewer of these have any detectors at all. And this is actually somewhat suggestive that we see that there is some dilution happening at the higher up on the red giant branch for these higher mass stars. All right, so the final thing that I want to talk about is the connection to rotation, which we've heard multiple times now. So on the red giant branch as well, there's this relationship that when you have higher lithium or higher rotation, you're more likely to find the opposite thing, but you're not guaranteed. So fast rotation does not guarantee that you'll have high lithium or vice versa. So this is now where I'm going to bring in those additional stars that we have in our sample. So again, a few previously known lithium-rich stars and stars where we knew either the core surface rotation, although our Subaru data does allow us to also constrain the rotational velocity from the width of the spectral lines. So this is a plot now showing what we measure for a full sample. So the lithium abundance on the y-axis and the rotational velocity on the x-axis. And we find, first and foremost, that like lithium, most of our stars do not have detectable rotation. Red giants are slow. But a key point here is, is that we do find that all of the stars that were previously known to be lithium-rich, we do detect rotation. Although the correlation between how lithium-rich and how fast is not entirely clear, we did detect measurable rotation in all of these cases. For the stars that aren't lithium-rich, however, there's no correlation that we really see. We see stars at all lithium abundances that have unmeasurable rotation, and the kind of the converse is true. Stars where we have no detectable lithium, we do in some cases see measurable rotation. But one of the things that's kind of hard with some of these plots that I really kind of want to focus your eye on is that 30 of the stars in our sample are all falling on this single point here, that we neither can detect the lithium in these stars and neither can we detect the rotation. All right, so in summary, we were looking at these Kepler stars to try to get a good sense of just how much variation we expect for normal lithium in these stars. And we do find a very large dispersion across all masses and evolutionary stages. Although generally speaking, we see that higher mass stars tend to have higher lithium abundances, and there's also some evidence that they may destroy lithium on the upper RGB. Very simple models can account for this just with the large amount of dispersion that we see on the main sequence. But one of the things I really want to highlight here is our understanding of the true dispersion of lithium and the impacts of rotation is still very much observationally limited. We don't actually know just how slow the majority of stars are rotating or just how low the majority of stars lithium are. So if we come back to this question of how much lithium is needed for a red giant to be lithium rich, I think you will not be surprised to know that we still don't have a very definitive answer. And I hope that is a great way to kind of lead into the future discussions we'll be having. Yes. So for this, okay, so the question was, did we also look at rotational periods? And the answer to that question was yes. There was many fewer stars that had those measured, and they were folded into the sample that you saw. But there isn't anything really that came out of that we didn't already see. I will pass it along to Leo.